Concrete, used extensively worldwide, has been vital to human development since ancient times. However, producing it in large quantities poses significant environmental challenges. Cement, the most hazardous component, accounts for about 8% of global carbon dioxide emissions. To address this, we propose an innovative concrete mixture that reduces environmental impact and enhances durability by partially replacing cement with supplementary cementitious materials.
Let's dive into our supplementary cementitious material. A prominent example is fly ash, which is a byproduct of coal power plant. Silica fume, another notable SCM, is derived from silicon metal and ferrosilicon alloy production. Additionally, GGBS is obtained during the separation of slag from molten iron. When this material partially replaces cement in concrete, they contribute to the formation of secondary generation of calcium silicate hydrogel, thereby enhancing the durability of the concrete.
On, let's keep an eye on our material selection. The criteria based on base case scenario and alternative case scenario. In the base case scenario, we opted for cement as the cementitious material, fine aggregate, coarse aggregate, and water. Point to be noted that water cement ratio here is 0.40, where cement and aggregates hold maximum of 25% and minimum of 75% respectively. In both cases, 2452 kg per meter cube total unit weight has been utilized. Our mixed design optimization process constitutes into four phases where the last phase turns out to be the ultimate one. Going through the first phase trial, we experiment with fly ash, silica fume, and GGBS. Here, fly ash remains constant, which is 20%. We keep the amount of GGBS and silica fume variable throughout the trial, keeping a close eye on silica fume. The more it increases, the more the value of D28 degrades. Constantly lower D28 creates lower permeability that eventually hinders the chloride penetration. As a result, service life increment is visible with better durability over the passes of time. In our second phase trial, we go with fly ash and GGBS. Here we can see constant increase and decrease respectively in case of fly ash and GGBS. In this case, D28 remain constant, which refers no ensurety of corrosion safety in the reinforcement. It also has adverse impacts on atmosphere. Going forward to our third phase, fly ash and silica fume are being used. Progression of the degradation in case of silica fume results into higher D28 value. Higher value impairs reinforcement in corrosion. So lowering of silica fume is advancing our mixture. From trial 2 and 3, increment in silica fume gives increase of 85.7% in service life score. For GGBS, the percentage is only 7.7%. In case of durability, silica fume gives rise to 85.76%, but for GGBS, it's only 7.765%. So we will use fly ash and silica fume as some supplementary cementitious material. Looking forward to even further, 38% of coil fly ash and 2% of silica fume is gotten with least environmental impact reduction score of 15.95% from the final mixture. Let's go to complete overview. In the base case scenario, we use 430 kg cement, 990 kg coarse aggregate, 860 kg fine aggregate, 172 kg water. In the alternative case scenario, we use 258 kg cement, 990 kg coarse aggregate, 860 kg fine aggregate, 172 kg water, and most importantly, 163.4 kg fly ash and 8.6 kg silica fume as our supplementary cementitious material. Now have a closer look at our potential environmental impact score, which includes global warming, carcinogenic, ozone depletion, ecotoxicity, and fossil fuel depletion, which eventually gives us the value of 15.95 score.
As we know, life cycle assessment help us analyze the environment impact of a material's entire life cycle, which includes its extraction, production, transportation, and distribution. And after analyzing each material, we have found an average environmental impact reduction of 15.95% from the base case scenario to the alternative case scenario. Individually, it shows the highest amount of reduction is in global warming, followed by fossil fuel depletion and ozone depletion. The reduction has happened due to the partial replacement of coal fly ash and silica fume as their production and transportation are less reliant on fossil fuel, emit significantly less carbon dioxide and any other harmful gases like chlorine or bromine. However, silica fume often has impurities like lead and chromium, and this may lead to comparatively less environmental reduction in ecotoxicity and carcinogenic impact, but these are justified with a massive increase in service life and overall reduction of environmental impact.
This mixed design tries to impact the least amount of environmental impact without compromising durability. Our project will bring us one step closer to achieve sustainable development.
It will ensure a resilient infrastructure resulting in a sustainable communities. It will utilize huge amounts of industrial byproducts and finally by reducing global warming and other environmental effects. It will be bold action against climate change. It's time for taking innovative steps in construction for the betterment of planet Earth.